Okay, this week we're going to talk about glaciers. Good and bad news is the good news is there isn't a ton of information this week to focus on, so that'll hopefully keep you from your heads exploding. But the bad news is there is a lot of terminology. I'm not a big fan of terminology, but unfortunately, when we talk about glaciers, there's features that we identify with different types of glaciers, and we use those features to reconstruct kind of what's happened in the geologic past. And so it's useful to identify those and kind of know their name. So there'll be a little bit of that, hopefully not too much, but we'll see how that goes. Okay, so what we got going on here is a little of this. So some misconceptions that we want to talk about is there was just one ice age in the past, and of course that's not true. There have been many ice ages in the geologic past. In the past 2 million years, there's been many, and so every 100,000 years or so, there seems to have been an ice age of some kind where the ice has been larger than it is today, and we'll talk about the different types, but we have ones that are kind of confined to mountain ranges. We'll call them alpine or valley glaciers. And these big ice sheets that kind of move across land masses and cover almost everything. In the last 2 million years, been a lot of those coming and going. But there's evidence that there's been large amounts of ice on our planet, 250 million years ago, 600 million years, billions of years ago. Of course, the farther back we go, the harder it is to kind of piece all that together. But still true. And if all the ice melted, including all the ice caps and everything, it would be like this awesome movie called Waterworld. Anyone seen that one? Okay, maybe not awesome, but of course that is not true. There would be a large change in sea level, pretty significant, but not enough to certainly cover all the land masses. Now, if you live on the coastline, potentially that could be a problem, but here in Arizona, we'd be safe and happy. There would certainly be some impact on society because lots of cities live near the coastlines, and they would be affected by a complete melting of all the ice, which would take a long time. So even though there's been an increase in the melting and there's concern sea level is rising, certainly not going to, rise 230 feet in your lifetime. If we did, we could kind of see the changes here. The dark black line here is the current, right? And then if everything melted, poor Florida is underwater, the entire state, and a lot of portions of the east coast here. West coast, because the coastline's different and a little more elevated, you wouldn't have that issue here. But there's been times where when the ice was more and it's pulling seawater and freezing it, that we had a coastline that was kind of like this red line here, where there's more land mass. And so certainly over geologic time, sea level has risen and fallen, and some of that has been due to increase or decrease in the amount of ice that we have on land. Okay. Oops, a little fast. North America was completely covered. That's not true. There's certainly some portions that were covered, but if we talk about the entire continent of North America, you can see from the diagram to the right that, places like we said, Arizona and southern states here, not even close to being covered. Still a lot of ice, a lot more than there is today, but not that the entire continent was covered in ice. So what is a glacier? So these are things that are forming on land. And so we call them ice sheets when they're forming these big, huge, broad features like Greenland or Antarctica. We call them alpine or valley glaciers when they're confined to the mountainous regions or the valleys. If they're on, the ocean, then they're just ice shelves or packs, ice packs. Those are not considered glaciers. We want them to be forming on land. And because they build up in thickness over time, they actually accumulate some mass, and the pressure and the weight actually allows the glacial ice to flow or move. And so glaciers are in motion constantly. Whether the end of the glacier is moving forward or backward has nothing to do with the glacier is constantly moving. It's really a supply and demand story, and we'll talk about that in just a bit. Okay, so how do we get glaciers? Well, we need places where there's a lot of snow. And so if we accumulate a lot of snow, and the trick to developing a glacier is you can't lose all of the snow in the summer months. You have to have some left behind so that the next winter we can add to it and we can expand the amount of snow that has fallen. And over long periods of time, years, sometimes decades, we can compact that material. And it goes through kind of this transition here where you see snow and granular ice. Firn is a common term that's kind of between the snow and the glacial ice. It's really a compaction of the snow over time and this kind of recrystallizing of the snow. So there's some melting and recrystallizing going on until we reach this point where it's glacial ice, has a lot less air bubbles in it than, let's say, just a bunch of snowfall. And it has recrystallized into these intergrown crystals that we can see. So when we see this, we kind of look at these two different budgets. And this is talked about in both the video and in the article. And it kind of talks about how glaciers form and move. We have a zone where we accumulate lots of material, snowfall. And then we have a portion that's in general lower elevation where we're losing snow and ice. It's melting, right? So if we have lots of accumulation, then we can advance our glacier, right? Because more stuff is being accumulated than is being melted over time. Our glacier will move, the end will move farther toward, in this case, this diagram here, toward the ocean or to the sea. The glacier, remember, is always moving, right? Because of meltwater at the base and gravity, it's moving down slope. Always. It doesn't matter whether the end is here, or over the years it recedes, or over the years it expands. It's always flowing, but we can determine whether it's retreating or advancing based on how much is falling and how much we're losing. If we get more than we take away, then it's going to advance. And if we take away more than we get, it's going to retreat. And so ablation is just a term in the article. I believe they called it that zone of waste. I think that's what it's called. Wastage. That's what it is. Sorry, the zone of wastage. So you have where you accumulate, the zone of accumulation, and the zone of wastage or ablation. They're both kind of, the wastage and ablation mean the same thing. So that's the part where we're losing stuff, and the accumulation is where we're kind of gaining stuff. So the key here is whether it's advancing or retreating based on how much we get. Our budget, and talks about that a little bit in the article too. So the flow, how these things are moving, once again, there's some overlap with the article here, but it probably explains it a little better. The idea is that with the pressure, right, these glaciers can be fairly thick. So the alpine ones, the ones that are forming in valleys and mountainous regions, tend not to be as thick. But once they, it varies depending on conditions, but 20 to 50 meters thick, that's pretty thick, 150 feet. There's enough weight that the pressure causes some melting to occur at the base here, and that water that moves along the base can help this mass of ice slip and slide down slope, and it'll slide over the bedrock. And then, of course, we have these different zones here where the upper part's very rigid, where we get our crevasses and cracks as it moves down slope. But below that, it's a little more plastic, so it's going to slide and slip over each other and a little more, it'll bend basically, right? Not as brittle as the upper part here. But the idea of the fluid at the base here is helping this thing slide over the bedrock. And so when they move, we can get this rigid zone. So the idea is that you see the bedrock has kind of bowed up here. And so the bottom part can adapt to that because it's flexible, it's plastic, but the upper part is rigid. So around corners or over hills, it's going to crack and fracture. And this is why we get crevasses at the surface. They don't go all the way down to the base, but they certainly can be fairly deep. Okay, so where do we find these glaciers? Well, we talked about already kind of the two places we see them. We get really big ones at high latitudes near the poles. So now we're talking Antarctica, Greenland, things like that. These are the places where we get these very large ice sheets. And when you read the article, you'll hear them talk about some of the thicknesses. We said that they can get fairly thick, but in these huge ice sheets that are sitting in Antarctica and Greenland, they're, up to 1.5 to 2 miles thick. You can imagine the mass of that, and the moving of that massive material certainly does some damage to the underlying bedrock. And we'll look at some of those features that helped us identify that glaciers either had existed there in the past because of the massive erosion or deposition that they left behind. So we have our ice sheets, and then we have the smaller ones that we're going to call, you'll hear the term valley glaciers or alpine glaciers. These are the ones that are forming in high elevations, so Alps, Himalayas, the Andes Mountains, things like that. This is where you'd expect to find these alpine glaciers. So when we look at these types, the alpine glaciers, what we're going to come to find out, and this goes back to this terminology story, is that the alpine glaciers tend to have erosional features that we identify fairly easily. And so even though both glacier types erode, do some erosional damage, and leave some depositional features behind, it will come to find out that the alpine is more erosional features that we'll have to kind of be aware of. When we get to the ice sheets, it's going to be more about the depositional features that you'll have to kind of look at. So for a lot of these slides, they're just kind of imagery and to show you what they look like, because that's kind of the idea, is you're identifying these features based on their morphology, right, their shape. And so one of the things that's common in both types of glaciers is something called striations. And you can see here that this kind of linear feature that you see on the bedrock here is associated with glaciation. And the idea is that as these massive weights, these ice sheets or ice glaciers that are in the alpine, as they move down slope, they're so massive that they're picking up debris from the bottom, loose debris that's cracked and fractured. Of course, those pieces get stuck in the base of my glacier because there's melting, and then there's freezing and remelting and freezing. And so it can accumulate a lot of debris at the base, and of course it's being pushed along and scraping the underlying bedrock. And it scrapes it fairly smooth, and it leaves these ridges, which we call striations. Once again, they can be in both types of glaciers because they're both massive enough, have enough weight, and accumulate enough debris at the base to cause these features to show up on the bedrock. So if you see those, it's a good indication that there used to be a glacier here. And this is some of the evidence that Wegener used way back when we talked about plate tectonics, when he thought about continental drift. He found these features in places where today the climate is much warmer. One of his ideas was that, this continent or this landmass must have been farther north or south near the poles, where it could have accumulated a glacier and has since moved to a warmer climate. That was one of the pieces of evidence he used for that. All right, more erosion stuff. So a cirque. A cirque is at the head of the glacier in an alpine region. It's kind of this bowl-shaped feature where the accumulation of snow and glacial ice is started, and then it moves downslope from there. So it's a bowl-shaped feature. We also have what are called horns, like the Matterhorn is a term you might have heard. It is an erosional feature associated with an alpine glacier. And is the idea that there was multiple glaciers on all sides of this mountain range that wore it down, and of course the peak was left behind. We get things called arêtes. These are ridge-shaped bedrock that separate two different alpine glaciers. You get a valley over here that's being carved and a valley over here. And then you get this nice ridge-shaped feature that's fairly sharp. Another image of a horn, indicating that there was glaciers on all sides. More images where you might be able to pick out some things where we would suggest that today, or at least in this image, it doesn't look like the glacier is here anymore or moving, but there's an old cirque right here. This ridge is an arête that's separating a glacier that moved down valley here and one that moved down valley here. On the other side, there's these were all glaciers at some point. There's a cirque there, right? Another identifying feature that's more global is this U-shaped valley. So one of the things that keyed people into the idea of glaciers causing some unique features was up in the mountain range where there's steep elevation, we have a lot of steep areas where water's flowing down. So streams tend to have a high velocity and they downcut pretty easily. They form really V-shaped valleys because of their downward erosion. And they would come across valleys that were very U-shaped, like this image on the right. And it was hard to kind of justify that that was cut by a river because we don't see that with rivers. And so the idea was this was filled with ice, probably hundreds of feet thick, and that whole ice sheet, as it moved down valley, sculpted not only the bottom like a river would, but the sides too, and turned it into a U shape. And another U-shaped valley. We can get what are called hanging valleys because of heavy erosion in different valleys, different depths of the glaciers. So you have a small glacier here and a very huge, thick glacier here. So this is much deeper, carving much deeper into the valley, where this isn't carving as much. And when they melt away, we have a huge valley here, but this little valley here. And so now the water has to fall down this elevation, a waterfall, in order to meet this other stream. But here, because this was so thick, it didn't have to carve down that far to kind of meet up with it and move down into that valley. What else we got for you? So there's another image of a lovely hanging valley. So this is what we would expect if we were not to see any glaciation, right? We would have a V-shaped valley. This is what we expect from river erosion, right? It's pretty sharp, pretty rounded. There's none of these kind of unique features that we see in a glacial valley. But if we fill this up with snow and ice over time, it turns into it. What we find is these V-shaped valleys get widened out into U-shapes. We get multiple glaciers coming down, leaving these arêtes in between, a nice bowl at the head of the glacier. And so when this finally goes away, we're left with these features. So if you come hiking up here and you're looking at these features, you're like, this is not something a stream would do. I've got a U-shaped valley. I got these bowls. I have these really sharp ridges we're calling arêtes. Got these unique peaks we call horns. Got hanging valleys. All these things kind of lead to this idea of this must have been glaciated. And so even though there's no glaciers here today, we could argue there was some in the past. I'm going to grab this really fast and see if this is useful at all. But here's some Google Earths of kind of what's happening, at least pretty recently, kind of right here in the Alps. And so you could see, you know, here is some snowfall for sure. And we can identify some glaciers here, right? There's a little bowl-shaped feature here, a cirque, and the glacier's moving down valley here, and then here's another one. There's a cirque here, a cirque here. There's a cirque even over here, probably one here. These are all moving down valley, and they're joining together into this one big massive glacier, and they're moving down valley this way. Right, so they come down valley, and eventually, of course, then most of the ice has melted and we just have debris. And some of the depositional features that you'll see, these lines that we see in here is actually rocky debris. We get rocky debris on the edges, and we get rocky debris at the very end of the glacier. And that is just all the material that it's pushing and eroding as this big, massive glacial ice thing moves down slope. Some of it is just plucked up, some of it is falling on top, some of it is actually being ripped up from the edges, or ripped up or plowed, right, from the edge, or even transported within the glacier. And so we can get these multiple depositional features. We'll talk about that, right? Let's see here. So the term that I just want you to really remember is till, because that's our general just catch-all term for any debris that is deposited by a glacier. Okay, so there's some other types that, you know, melt water and other sediment, but the till is kind of the general term. If we see a bunch of debris, we say, hey, that was pushed or deposited or torn or by a glacier, we're going to call that till, because the till can be piled up into different shapes. And what we see for alpine glaciers, although we had lots of erosional features, right? Cirques, arêtes, horns, all that. Moraines are these ridges of debris that have been deposited by the glacier. And they can be on the edges. This is a moraine. There's one on the other side. You can have moraines here in the middle where two glaciers meet. And you can have moraines at the end of a glacier. And of course, they all have their names. You have a lateral moraine, a medial moraine, an end moraine. But they're still all moraines. There's these piles, ridges of debris and rock that have been pushed or torn as the glacier makes its way down slope. And so the end moraine, a lot of it is either on top, that gets trapped in, or it gets transported from the bottom. And as it melts, it deposits this big pile here. This end moraine is useful because we can find these today, and it tells me how far the glacier has moved in the geologic past, because the farthest end moraine I can discover would just tell me that's as far as the glacier has ever gotten. Okay, and so that can be useful for piecing together the history of different ice ages and things like that. And so here's some better imagery that talk about, right, we have these medial moraines, lateral moraines, and this is kind of what they look like. More pretty pictures that show these deposits of material and in the glacier itself. More pretty pictures. And then, okay, so for glacial, for alpine, we're talking those erosional features that we mentioned you should know, and really just that one type of depositional kind of till ridge, right, that comes from that. For these ice sheets, we tend to see lots of depositional features and less erosional features. Now, striations still exist here, except they would cover a large area. These ice sheets cover hundreds of square miles, and they move over almost everything. And as they do so, they scour the landscape, and they leave the marks just like an alpine would, but it wouldn't be restricted to a valley. It could cover large, broad areas for the same reason, right? Massive weight, moving along, dragging pieces at its base that scratch and scour the bedrock beneath it. Here's where we get a lot of craziness. There's a lot of depositional features that are associated with these ice sheets. Now, we certainly get the moraines because there's still this pile of material that's being transported, and at the edge of the glacier, it's being dumped. We call that the end moraine for sure. But there's some other features here that I'll run through really fast. Drumlins, eskers, kettles, recessional moraines, end moraines, holy Toledo. So we're not going to go through every one of them, but the few that I think are important we'll kind of touch on. So let's go through those. So drumlins are these very unique piles of till, but they're parallel to the direction of movement, not perpendicular like a moraine that would be piled at the end. And they have kind of these teardrop shapes. And so we can identify those to give us direction over these large ice sheet movements. And so this is kind of what they look like in real life, or maybe over here. And then, from a topographic point of view, all these little weird linear features are drumlins that tell us that there was a flow kind of in this north-south direction here. Okay, so they're a useful tool to give us direction. We have something called an esker, which is kind of this snake-like deposit of gravel and sand. And so the idea is that under some of these glaciers, we actually have streams that are flowing, and they are depositing sands and gravels. And of course, when the ice sheet melts away, we have this kind of little hill left behind from where the stream used to be, just called an esker. Okay, so from stream and meltwater coming down, in some cases they run for long distances, like the image to the right here. We have something called erratics, and these were something of a puzzle until they figured out what they were, but the reason that they're unusual is they're usually very large boulders that are found in the middle of nowhere where there's no other boulders. And when we look at the composition of the boulders, the source area is usually hundreds of miles away. And so if we would look at this rock and say, oh, look, it's a granite, so there must be granite around here. Nope, there's no granite like it, but there is some 250 miles to the north. So what type of geological thing could move that boulder that far? Well, the idea was that it got plucked or torn or dropped into this huge ice sheet. It transported it all along, and then when it melted, bloop, it just dropped where it is. And this is how it got transported so far from the source. Another indication that there was large ice sheets in the region when you have these erratics. And then lastly, there's just a few little diagrams that show you how did we puzzle out that there was multiple big ice ages in the geologic past. A lot of these depositional features tell us. They tell us how far things have gone based on some of the moraines that we see, these end moraines that we talked about. And so here's a bunch here that have been mapped out that give us some indication of different events that have occurred based on some end moraines. Of course, it's much more complicated than just looking at a little ridge and going, oh, that must be the end, because some of them have been obscured or they have been overridden by other events. And so you have to kind of piece those together. But certainly they give us some information about how far south, at least in North America, the ice ages went. Just another image that's kind of showing you all the features, right? A kettle lake is usually where you have debris, but there's a big block of ice trapped in the debris. And then, of course, the ice melts and all the water is kind of sitting in this depression where it was, and we get a lake. Of course, we have the eskers we talked about. We have erratics we talked about. Drumlins we talked about. End moraines and recessional moraines are just moraines that tell us as the glacier was retreating, it left some, as it recessed, it left some till, these mounds of till behind. Okay, and then, the last thing I'm just going to touch on is why do we have glaciations? Well, it's complicated. There's certainly lots of factors that can influence our climate and determine whether we have glaciation. So a lot of it is about heat that the Earth is either absorbing, holding, or receiving. And so there's certainly a lot of factors. But one of the things that we think, at least, that has happened let me go back to right here, that has happened in the last 2 million years, because it was pretty cyclical for us in the last 2 million years. We'd have ice age and then recession, and then ice age and recession. And so what they think was going on is that variations in the Earth's orbit is really dictating how much heat radiation we're getting from the sun, and it's episodic. And so the three things that were kind of tied together were how the Earth's orbit changes over time. It's a little more circular, and then it gets a little more elliptical, and then it goes back to circular. And this seems to happen every 100,000 years or so. So when it's more elliptical, there's a long period of time where we have less heat radiation, and we can cause the planet to cool down more, accumulate enough snow so that it doesn't melt in the warmer times, and then we can pile more on and pile more on. The other thing that happened is the tilt of the axis changes, and that has kind of a repeating pattern. And this wobble or precession of the axis has a repeating pattern. And the idea is that when all three of these kind of line up every 150 to 200,000 years, all three can really add to a cold period where the Earth's climate has been changed enough that we can accumulate lots of snow. And then once you get glaciers that get pretty large, then the white snow reflects a lot of sunlight, and that can help spur on the growth of these glaciers until we get kind of a period where we get a little more heat radiation, and then it starts to melt, and that warmer period dominates. And so they call this the Milankovitch cycle, because he was the guy who kind of came up with this idea that these three things were all tying together to give us these kind of cyclical ice ages that we've seen in the geologic past, at least in the past 2 million years. So harder to kind of piece together the really old ones because, things were so different back then. Sometimes it's just has to do with where the land masses are. One of the reasons we think that there was a big ice age 250 million years ago was that all the all the continents were together in our huge, Pangea, and that whole mass was a little to the south where it's colder. And so without landmass, I can't grow glaciers. So just like in Antarctica, I have glaciers. They grow, but once they hit the water, they don't grow any further. But if I have a landmass that's even bigger than Antarctica is today, like Pangaea, they could grow, and they could grow really big. And so that was one reason why glaciers might have been able to grow fairly large, 250 million years ago. So, and of course, like I said, there's greenhouse gases and other things that come into play. But for the recent past, we think that this is one of the things that are initiating this kind of ice age cycle that we've seen in the last 2 million years. And, oh golly, there you go. So that's all I got for you. All right, so I thought this was going to be really short. Sorry, it's a little longer. But a lot of terminology. Just make sure you kind of look at those images that talk about identifying the erosional features for alpine and the depositional features for the ice sheet ones, and you should be good.